So, good morning. So, we will start from lecture 12, that is establishing zero waste biorefinery for crustaceans and shellfish. So, what is the protocol for establishing a biorefinery? First, we need to know about the biomass, what are its properties and what are its requirement. That means how to stabilize it, how to preserve it, and then second one, what is your target bioproduct, what you want to achieve out of it and what is the specification of that. Yeah. Then you make the inventory of processes and the product and the technologies. Then you try to club it together and then to make the process workable and then do your cost benefit analysis. Take an example of if you have to assemble a computer or assemble a car. Yeah. Car is having multiple engines, you have tires, you have engine, you have fuel delivery system, fuel tank, yeah, and output is efficiency and all those things. So, how you assemble that, very similar approach is for biorefinery. So, I was talking about lumpfish or the small fish which is used to eat lices in salmon aquaculture farm. So, they look something like this, as you can see small blue fish, yeah. So, these are the small fish which are used till certain weight and each and every species is manually vaccinated so that they do not impart disease into aquaculture farm. And after that they are also known as cull fish. That means once their job is done, they are either killed or if you leave it into open water and they go big. Yeah. So, again there is one short video or short of presentation here which shows how we can use the whole lumpfish itself for valorization purposes. So, whole fish is grounded, added alkali, centrifuged, then you get lipid on the surface. Yeah. After that, if you remove the oil, because this contains very low amount of oil, you hardly see anything. Protein precipitated with a hydrochloric acid, and this is what you are going to do pretty much today. You already have biomass here, and then after that whatever is left over residue is the collagen extraction. So, collagen extraction is acid soluble fraction of the protein and then you get slightly whitish in color. Yeah. And then as you can see collagen is started precipitating and this is the white color collagen what you get. Yeah. So, in this is what pretty much of the biomass, whether you use a whole biomass or you use a side stream, is both the same thing. Fish, you add an alkali to extract the protein, you have residue, alkali whatever you extracted, adjust the pH to 4.5, 5.5 or 3.5 depending upon isoelectric point and then protein precipitates, that is A protein. Leftover residue, you wash it to remove the acid, to remove alkali and then you add acid to it, do again the extraction, now you get acid soluble protein. That is why I mentioned Osborne classification. Yeah. Majority of the protein is alkali soluble, that is why half of the reference in literature is alkali extraction, that is sodium hydroxide. pH 8 to 12 and you adjust the pH. It is not you have to make a solution of 0.1 molar and then add to it, or else even if you are adding a water and you adjust the pH between this area. Yeah. That is the purpose, either you make a solution, add the stuff to it, or if you have water added in and adjust the pH to 8 to 12. Always adjustment of pH is done either by 0.1 molar or 0.2 molar, not to use very high level of acid. Yeah. You can use higher level of concentration of acid provided you are just using it for adjustment of pH. Yeah. So, this is what we pretty much covered other day, and then you have different technologies, whether you use it for during collagen extraction or you use it during protein extraction, or if it is having high lipid, so you have to remove the lipid first. Some of the suggestions came in other day for using microwave to separate the lipid or squeezing it or to cooking the whole biomass. to separate the lipid and subsequent extraction processes. Yeah, there are multiple options are there. And when you do research, you investigate number of different options and then come out with the best solution. Yeah, this is very similar if many of you travel to Rourkela for the first time. So, how many routes were there from Chennai to Rourkela? 10 different ways of coming here. Easiest and cheapest one was walking all the way from Chennai to Rourkela. Most expensive one was to hire a private chopper and land straight into Rourkela. Yeah, walking, economical, time consuming, conventional process. Hiring an helicopter, landing into Rourkela, quickest 35 minutes and most expensive. Yeah. So, all those things are exactly the same way. It is not that somebody is doing PhD and or completed a PhD or a postdoc or a professor, they are only researcher. Everybody is a researcher and at some point or the other. Yeah. Okay. So, that is one. Now, again coming back to the same stuff of fish biorefinery or seafood biorefinery, is one is how do you have a fish? You can preserve it by using a salting technique. Many of you who are aware of seafood at domestic level or at you have seen in the coastal places, sun drying, as I mentioned, you dry the whole fish, yeah, then separate the oil and then powdering it to get the protein. That is another way, that is dry way of doing it, and I will cover this one when we go into ingredients and products and technologies. Smoking, long, hot and cold, these are all different techniques how the fish is processed. Rapid freezing, that is at lower temperature, or cold storage. Yeah. And then you have number of different new techniques, and some of these techniques we will be covering it as we move forward. Whether it is cold plasma, you have seen the demonstration of cold plasma. So, I will cover the full theoretical part and lectures related to cold plasma, how different applications can be made. Some references for ultrasonics. Irradiation, we will not cover it because you would have studied a lot about food irradiation, gamma irradiation and other places. Some countries they do not or some consumers they do not like radiation, and in India there is a Bhabha Atomic Research Center where a lot of food radiation work is carried out, and that is one. Bit on pulse electric field, high pressure, and some of those alternative to chlorine. And this is again the very simple process. You have fish waste or discards, you make silage or you preserve it, that is stabilization of biomass, and then after that you go for extraction process. Yeah. So, establishing a technology for biorefining or bioprocessing, biomass, stabilization, stroke pretreatment or extraction, and then you have end product. So, this is all what you get different side stream and how it can be carried out. So, number of different techniques are there, and half of those techniques have been traditionally used for non-fish application, but you can replicate them on seafood. Now, coming to the shells. Yeah. So, if you look at the shells, these are the statistics, and if you remember lecture number 8 or 9 when we are talking about waste valorization. First one is to quantify waste and see how much waste is available and how what all can be extracted. So, these are the statistics as I mentioned earlier from BIM boardishmara.ie. This is Irish Seafood Board, yeah, which estimates all the waste processing and help different industry to run those businesses. So, contribution is euro 1.3 billion for GDP for Irish seafood industry, and you can see number of companies, number of processors and number of aquaculture sites and total number of people employed. Yeah. For given size of the country, this is quite big numbers. Yeah. And where are the majority of activities located? Now, with this the type of side stream comes is only the shells which does not contain chitin chitosan. This is a bigger problem because how do we dispose them? Because small amount of meat is attached between those two shells, and because of that it is classified as category 3 waste. That means which can create disease and can have lot of food poisoning. So, it has to be discarded according to a certain regulations, very similar to dead animals. If you are working in veterinary and dairy farm, there is dead animal, how do you dispose that dead animal? You do not recover ingredients out of it. Yeah, it is very similar, but till the time it is in food processing plant, it is still a food ingredient. The moment it comes out, it is a waste, then goes through a completely different regulation. It is very similar till the time you are eating a pizza, half eaten pizza, you keep it on a plate, it is still a food. The moment you put it in a bin, even your bin is having all other food item, you see it as a waste. Yeah, similar example. And then you have scallops, shells. So, it says sales volume, production units and amount of waste they generated. If you take the quantity, where is the quantity written? If you take total quantity in terms of values, the waste generated it enormous. Yeah, if it is 30% is wasted, 30 to 50% is wasted in terms of metal, you can think how much of waste is generated. Yeah. So, that is one, and then this shows the shrimp processing, what you have done a bit, and this is done with our own postdoc, he is working on that particular Impress EU project. This is the final product what is left over. If you will see, okay, I will just mute this volume. This is done in a lab over there, very similar what you guys were doing. Shrimp added in with, here the work was done with acetic acid or pepsin, the number of different enzyme options are there. So, after that, and this is actually demineralization carried out by using hydrochloric acid and ultrasound. This is ultrasonic system which was carried out to improve process efficiency, deacetylation, that is again 50% NOH high temperature, and then you are left over this product as a chitosan. Yeah, and whatever water was coming out of it, that is again for the protein, and if you will see, it is not very clear here, this white droplets, these are the protein which will be precipitated for obtaining protein, and leftover water is going to go to our other partner to grow duckweed on that particular biomass. Yeah, or to grow microalgae. So, whatever comes out the best one, and that will establish complete biorefinery, blue circular economy. Yeah. So, what you are seeing is really application, similar type of experiment what you are doing over here. So, that is another one is whelk shells, that is again the snails. Yeah. How many of you eat snails? Okay. So, snails are eaten as different forms, like whole snail is cooked and muscle is separated. The waste is shells, and these shells, they do not contain chitin or chitosan, they contain very small quantity of chitin. If you will see here, shells, this is exactly what you guys carried out here. Yeah. Well, this is again from our lab, and then is incubation with NOH or alkalis. Here the stuff is reversed. Yeah. That means alkali is used or protease enzymes are used. That means deproteinization first, followed by removal of minerals. So, it can be either way. Yeah. Separation and washing, and he is a postdoc from Indonesia. His name is Johnson. Yeah. And then once I will just move a bit faster. Oh, sorry. So, once you separate it, then we are extracting the protein, whether shell contains chitin or very small point of chitin or a protein, that depends how strong the shells will be. And this is what you will see, you are seeing all the bubbles, how these shells were completely dissolved. Yeah. And there some special stuffs were added in, and within shorter duration, this was completely dissolved like that. Yeah. This you won't have seen this one complete dissolution when you were doing the experiments here. Can you guess the reason? Do not say the acid is different, no, not because of that. The reason was because it was not having much of chitin or a protein, whereas prawn shells or your shrimp shells or crab shells, they are harder, they have large amount of protein and chitin in their network. That is why you will see lot of that material, that is why it was bit more flexible, not hard, and that is the way you can obtain the calcium. And I think the ingredient, if it is right, so you will have calcium chloride or calcium acetate, whatever acid was used. Yeah. So, it is the simple process, and then how you improve the process, that again depends upon application of different technologies. So, I am coming back to the slides which we covered briefly before on shrimp. Harvesting, storage, your pre-treatment stuff, thawing and washing, again stabilization, pre-treatment, cooking and market. Wastewater, drying, milling, demineralization, deproteinization and deacetylation. Yeah. I tend to repeat a process so many times, so that you will remember by heart, then you do not have to write it and do it. Yeah. And then to improve these two processes, either use ultrasonics, microwave or combination of these technology, use fermentation or enzymes. So, even you can use a microorganisms which can eat those proteins or eat those chitin, that is chitinase, if you are interested only in protein side of it. So, there is a number of ways of doing it, and these two processes can be named as biological processes, yeah, compared to mechanical, chemical or physical methods. So, you can get chitosan. So, this is what you saw, that white color box, chitosan, how much was obtained from 1 kg of biomass. Yeah. What are the side streams you are getting? Mineral rich extract, the water which is left over will contain certain nutrients and certain heavy metals. So, that is fractionated to see whether it is usable or it has to be discarded. Protein rich powder to obtain shells protein, and if you make a peptides out of it, and these peptides have very good bone recovery and bone properties, bone that is all joint health and all those type of anti-inflammatory properties are there, because they are coming in with from shells, and they have a strong binding with proteins and potassium or phosphorus within the bone structure, and you have a strong alkaline water, which you get your proteins, minerals and pigments. The reason why pigment step was removed even from the shrimp, what you saw in a short video, the reason was the moment we remove pigment, we need to add certain organic solvents. The purpose here was mainly to target chitosan and protein plus minerals. Yeah. If we have to go through the pigmentation route, then we have to use through supercritical or some other technique, if the intention is to get the pectin. Yeah. So, in biorefinery, it all depends upon what type of main products you want. Yeah. So, with this talks about your shrimp. So, if you will see here, all the water which is coming either from the shells or from cooking, all these things can be valorized. So, as you can see there, in reality how the circularity is added into different process line. Yeah. Majority of the literature, what you will see for chitosan production, it says shells were obtained from A, B and C, clean shells, freeze dried or milled shells and chitin yield. There is no reference of what is done with the wastewater, what is done with the protein and other one. Yeah. But now the shift has focused towards zero waste and establishing complete biorefinery, valorizing every biomass whatever is produced along the chain. So, that is why system is slightly changing. So, this is one. Second one is related to crabs. Yeah. In terms of crab, whether crab is whole crab itself is a waste, this is again repeat of what you saw briefly previously, right. And then you have a processing where you have for direct commercial sale, that is simple. Unusable ones you get different processes to obtain different products. Yeah. So, do you have any questions? It is quite similar, only the biomass is different. Any questions or any doubt you have? Because when I start asking question, then it will be a bit of problem. Yeah. So, if you have a crab, whole crab along with the shells, you recover meat. If it is of not the best quality, it's best for feed or animal purpose. White meat, processed, fresh, frozen, pasteurized or canned. That is normal product what you get. Other one, mixed meat, brown meat, tertiary processing, ingredient for paste, pate, snacks or cakes or different product. This is all your product development side of it. Other shells which are not used, you mechanically or separated, because here your intention is to crush everything, or directly to use a protease enzyme into unsaleable crabs and get the protein hydroslate out of it. That will be the easiest way of separating the shells with the liquid biomass, that is protein. And then you have clean shells, and then you go for chitosan production. Yeah. And how many of you eat crabs? Whole crab, processed and cooked. Yeah. So, based on that, you can again go for simple process for extracting chitosan. So, as you can see, chitosan can be as high as 14% of dry shell. Yeah, is a quite significant amount of chitosan you can get out of dry shells. Yeah. So, if you do not have any question, I will move forward. Now, this is the third shell, that is whelk or snails, and lot of snail farms are there. And I will be very honest, before this I was not knowing that snails are also processed. I was knowing in seafood only fish. I am talking about 7-8 years ago. When you go into different coastal areas, then you will see what all has been processed and what all is being consumed. The simple process for whelk is obtained, they are washed, manually segregated. Any shells which is having some stains or something on the surfaces, as you would have seen when you go to the beach to collect nice looking snails, or what do you call that, out of shunk, what do you call that? Shunk, right? Okay, the same word in every language, good. The shunk, and some places they have white tiny spots are there on them because of different damages. Those shells are discarded. Yeah, that accounts for 10 to 20%, in some cases up to 30% of those shells along with meat are discarded. Then that is, meat is removed either by cooking or by cooking in a brine solution. Yeah. And that meat is sold in a market. So, the waste product here is your shells, which also contains almost bit of meat, shells and some meat residue. As you can see, this is a snail and meat is recovered. The guys who are working on this, they only love seafood. Yeah, he's so keen in getting all the meat. Any extra meat he extracts it and is happy for that. So, this much of quantity is processed every year. Yeah. Out of that, 20% of meat and this much amount of shells and residue goes as a waste. You can see amount of quantity it is having there, right? And then in these processes you have a cooked wastewater, and when it comes to cooked wastewater, this contains salt plus meat in it. Yeah. The process was handed over to industry as whelk, STOCK, stock cubes. How many of you have used stock cubes? Small vegetable cubes are sold in a market. You just add it into the curry to get the flavor. Yeah, small Knorr and different brands vegetable cubes are there. Similar way, stock cubes are available for different products. So, all the salt solution can be obtained here. Other one is cooked water going through a membranes processing. Yeah. Sorry. I have to, yeah. So, membrane processing to segregate the protein based on your ultrafiltration, microfiltration, nanofiltration or reverse osmosis. Yeah. Microfiltration is something like sieving to a micron level. The normal sieves are also 10 micron, 15 micron, and some of you would have used HPLC or so, they are 0.25 micron filters. So, that is the membrane. So, microfiltration get rid of all the large chunk of protein. Then you go for ultrafiltration, but this is done after microfiltration, where you can separate based on the molecular weight. Proteins, what is the molecular weight range of proteins? They are pretty much more than 50 kilodalton and up to 100, 200 kilodalton. So, that proteins are separated. Then you have your peptides and then bioactives, and the salt molecular weight is in just few daltons. Yeah. So, based on that, biorefinery process can be established. Any questions so far? So, in a similar fashion, whatever you obtain with a wash water or a side stream, you still have protein or lipid, and this water goes for duckweed cultivation. So, this some of the details of all these work which is ongoing, and ongoing in the sense lot of research has already been carried out, lot is already there in the literature, but all this thing is happening to establish a full circular economy. This is again I am repeating the website, you can have a look, and if you have any questions you can contact those people and they will be happy to answer your queries. Yeah. So, with this completes your valorization of shells and crustaceans. Now, the question was yesterday whether we go for demineralization or deproteinization. Demineralization or deproteinization, which one is the best one? First we should remove calcium or first we should remove the protein? In your opinion, what is the best? Do not worry about this standard data. So, the work which was carried out here, deproteinization first, chitin yield, and then creamish white, demineralization, this one, that is chitin produced through DPM sequestration, that is deproteinization followed by demineralization, demineralization followed by deproteinization. I said other way around. You can see differences in the color and standard chitin. Which one do you think is the best? If you say A is best, then why? The simple stuff is, what is easier to do first, deproteinization or demineralization? You should eat fruits first, or you should eat main course first and then fruits, or you should eat your what you call tiffin items first followed by the main course. Yeah. If you go in wedding parties, especially in the north, you have all those pani puri and all those type of snacks are there, then you have main courses there. Some people they eat main course, then they go in sweet dish. Yeah. Some people they go first in a sweet dish followed by the main course. Yeah. So, similar type of approach is here. The reason is why most of the cases demineralization is done first, so that you are reducing the volume, yeah, and stiffness of the material. But if you are grinding it, then it does not make a difference whether you go for deproteinization or demineralization. The purpose of demineralization directly is, if you are able to break the shells or by using acid, it makes things easier then. Yeah. Okay. So, both the processes are applied here. Second thing is deprotonization is done first in some cases when you are not using advanced technologies. Yeah, if you are using a microwave and you are putting in a shells in, because of minerals and all, it will cause a lot of spark and other stuff. Yeah. Any questions so far? Is it all clear or nothing is clear? Okay. So, how we can do complete shell biorefinery? Yeah. Shrimp, how we can clean these shrimp? Think you have bought a shrimps or any fish at home, first you clean it. Either you clean it with the normal water or chlorinated water, right? Chlorine containing water. Second one is sorting or grading. Then processing includes beheading, that is removing the inedible portion of shrimp. You peel it, cooling, and you get shrimp meat. Yeah. How difficult is to get shrimp meat when you have shrimps from there? It's quite difficult to remove the shells from the shrimp. Yeah. Think of the lobster, it's even difficult. So, if the moment high pressure is provided to these samples, high pressure processing to certain pressure, it becomes easier to remove meat. I will show you a very short video the other day. Maybe when we go for the processing, right. Then clean, dry, grind, you remove pigments. Yeah. What type of pigments are present in shrimp? Astaxanthin, and they are classified as carotenoids. Yeah. Pigmentation by using supercritical. So, what you get? Pigments and other lipid fractions. Yeah. Once you have this lipid fraction, leftover biomass goes for subsequent extraction of proteins and other elements. Yeah. So, you have this, remove it and you get your astaxanthin, right. Now, once you get your lipids, pigments and astaxanthin, leftover biomass is subjected for demineralization, washing, yeah, deprotonization by using alkali, washing, residual water, and you get your chitin. Yeah. So, this is a complete biorefinery of shells. Yeah. Do you think anything is missing from here, or is there any mistake in this process? No? Okay. So, once you have all this, and remember when supercritical CO2 is used, that is in tune of 100 to 200 megapascals, right. High pressure conditions are used to generate supercritical fluid extraction. That condition is also good for advancing or enhancing demineralization processes, because shells are already disrupted. So, all these steps, any of the technology done will have a subsequent effect. Yeah. So, you might conclude shrimp shells directly extracting chitin from here without having supercritical extraction, or with the supercritical extraction you have different recovery yields, is because of this can be considered as pre-treatment as well. Yeah. And by doing so, in supercritical CO2 extraction system, you are also able to reduce the microbial load or microbial contamination of these shells. Yeah. Now, this is what shows how we can use the whole shrimp for a number of different products. If I ask you to identify the type of product we can obtain from here, from this biomass, A is your food item, yeah, that is your meat. Yeah. As you can see with the color coding, this is meat production. Yeah. Second one is astaxanthin, yeah, pigment. You have chitin or chitosan and proteins from here. So, complete valorization of this will yield you A is food, B is your astaxanthin, that is nutraceutical or pharmaceutical compound. You have protein which can further converted into peptides, that is your again ingredient. Chitin, chitosan for either for biopolymer application or for antimicrobial activity or for as an ingredient, yeah. 5 ingredient. What else we can get? The minerals, which is again related to CaCl2. Calcium chloride if you are using hydrochloric acid. Calcium acetate, calcium citrate, and if you go and look into the market and you will see all these ones are sold as a separate entity. Calcium chloride is anti-caking agent used as a filtering aid. Calcium acetate and calcium citrate, they also have some other medicinal or medical applications. At the same time, calcium citrate, calcium acetate are also can be used as an ingredient for chicken feed, where you have to add calcium to it, or fertilizer, yeah. So, this makes your full biorefinery related to shells. So, this shrimp can be converted to your fish or crab, pretty much the process remains the same. The conditions will vary depending upon the biomass, yeah. So, this is your deacetylization and chitosan production. Now, this is slightly complicated version of the previous one. Shells, astaxanthin, protein, calcium carbonate and chitin. This is what it is present in shellfish waste, yeah. Drying and grinding, you use 1:20 of hydrochloric acid, yeah. Here 1:10 was used, because this was supposed to be scaling up version. Our target is to reduce it to 1:5 so that we do not have too much of chemical there, but again we are compromising with the quality of the end product. Centrifugation conditions, yeah. So, what is the difference between RPM and G-force? You should never replicate centrifugal technique based on RPM, yeah. RPM can be higher, but G-force is the one which is to be replicated, yeah. Do you know the difference between G and RPM? Revolution per minute, yeah. If blade is a smaller length, in 1 minute it will do how many rounds, right? If blades are smaller, in 1 minute it will do more RPMs, yeah. RPM means point to point. If you have this circle, this point, how many revolution it will take in 1 minute, yeah. If you have a smaller circle, in 1 minute this point will take how many rounds, yeah, compared to this circle, yeah. This will take less number of revolution per minute compared to this one, yeah. So, RPM is not the one which is to be replicated. It is the G force, that is gravitational force. How to measure of the centrifuge? If you see the centrifuge, there is always a shaft. You measure the length of the shaft and based on that G force is calculated. That is why the windmills, they move so slow and they produce large amount of electricity. They are low RPM, but their G force imparted is higher, yeah. Okay. That is the difference. So, revolution per minute or G force. If you would have published paper, always the first thing a reviewer will ask you to write a G force, not the RPM, yeah. We do present RPM, it is just because we do not want to tell what was the G force, as simple as that. It is something like fan setting 4, that means what? Regulator setting 4 means nothing. Mixer grinder, regulator setting 3, isn't it? If suppose the mixer grinder is having only 2 regulator setting, high speed, low speed, those are no units, yeah. So, that is why you have to be very careful what you report and what is used. Then you have mineral rich astaxanthin supernatant. That is another reason why acids are used, because they are pretty much stable in acidic condition. That is why acidification. Then dilution, ultrafiltration system to get your calcium chloride, water, bit of hydrochloric acid and astaxanthin. Yeah? This is process number 1. Second, process number 2, after centrifugation, you have your pellet. This is pretty much what you have done. Yeah? Neutralized to pH 7. Now, why you were washing the shells yesterday after doing demineralization, you were washing it? Why? Mike? Yeah.
To remove the excess acids.
If acids remain there, what will happen? That is correct, yeah?
Like it will react with the upcoming NaOH. So it is better to remove it.
Okay, that's correct. We wash the acid because so that when you add an NaOH, yeah, it doesn't matter, you may have to add additional NaOH, but the problem is the moment HCl is still present, if you are not washing it and you use NaOH, instead of 10 ml you may need 15 ml, yeah, to get to that pH. So that is not a problem of having additional NaOH. The problem is it will form NaCl. Yeah? When NaCl is formed, and this will precipitate along with your stuff. So your chitin purity will be impacted. Yeah? So that logic was of washing was only to reduce the usage of NaOH. That is also not a problem because you are adding additional water, but purity of chitin or chitosan will be impacted. Yeah? So any of the process, if you see it, even this process or any literature process, if you have the question of why and what has been done, why it has been done, then you will have your all the ideas clarified each and every step. Yeah? So you should have at least 15-20 questions coming up with this particular process. Yeah? If you ask those questions and they say there is no point in doing it, so we do as reported process and slowly we eliminate the steps so that we make it very simple process. Yeah? Now, once it is washed, and remember when we wash it, this wash water can go back to this water because washing one will also contain certain amount of calcium and other salt. Yeah? Sometimes when you do filtration, how many of you make tea with a tea, not with a tea bag, by use or normal tea? Yeah? You boil it, you get your tea. The spent tea, if you boil it again, you still can recover some tea, right? So that means all the residual portion can be extracted out of it. So neutralize it to pH 7, filtration and drying system, then you go for deproteinization. Yeah? And then same centrifugation, protein rich supplement and proteins obtained. Yeah? Raw material, physicochemical properties and stuff related to input and output and what is economic cost associated with it. Yeah? Then once you obtain a pellet, then you wash away alkali. Why you are washing the alkali here now? To remove extra proteins out of it. Then you get your chitin. Yeah? Chitin is converted into chitosan, and chitosan is having good solubility in water, is just because deacetylation, that is strong alkali of up to 50% of NaOH heated for 2 to 3 hours to get chitosan. Yeah? And this is not a rocket science process. This particular process you can find it in a documents back to 1980s, 1990s. Yeah? Okay. So the advancement done is how we add technologies at different point. So running this full biorefinery process will take at least 24 to 48 hours. Yeah? to reduce the time of this to 2 to 3 hours. We change the concentration and we elevate the temperature. Usage of temperature, you have to be very careful. If you use very, very high temperature, the molecular weight of chitosan won't be high, which cannot be used for biopolymer application. But you can have low molecular weight chitosan, which are having lot of medicinal and pharmaceutical properties, called as oligochitosan, that is chitosan with a shorter molecular weight, or oligochitopeptides, peptides in the sense having a peptide, short chain chitosan, which will have other biofunctional properties for different applications. Yeah. So, this is what a cell structure looks like. So, whether you have blue crab shells or you have spider crab shells or any of those biomasses, yeah, this specific type of blue crab shells were opted from Italy, because we have Italian partner working on the project, and they get this blue to get what type of pigments were present in it. So, since we were only interested in to get those type of pigment, we went through a classical way of doing the freeze drying. We wanted to preserve the bioactivity of those pigment, extraction, and somebody was talking about deep eutectic solvent the other day. Yeah, deep eutectic solvent in a simple way is the mixture of solvents to get multiple properties together. Yeah, that's the meaning of deep eutectic. It is not a special type of solvent. If you are having alcohol, acidified alcohol, that is one of those deep eutectic solvent. Yeah, it is a word which is used. What type of solvent is water? Yeah, water is also a solvent. Yeah, and solute. Yeah, definition is solute and solvent. Solvent is any liquid which is used to dissolve solute. That's it. Yeah. Now, deep eutectic, that does not mean is a special type of a novel solvent. You have to buy it and do it. You make your own one. There are multiple number of combinations are there. Acid with choline chloride or with cysteine, they all have different properties which improves the extraction efficiencies. So, that is the only difference between a single solvent or combination of those solvent. So, this one, and then different techniques by using either ultrasonics or extraction. Now, these are the things what you have to work on. Extracting solvent, combination of natural deep eutectic solvent, or if you look into the literature, you will see, oh, I will use NADES solvent. Yeah, you know, is not tennis player NADES. Yeah, it's just natural deep eutectic solvent. The beauty of scientific research is lot of different types of abbreviations and names are used, which are often which confuses people. Not confuses, we get intrigued about it. Yeah. The thing is, if you are able to understand, you think, it's easy. Yeah. For you all, clearing 10th board exam, how difficult it is now at this stage is easy, because you have done it. Yeah. It is easier if you know it. So, it's better to understand in the simplest language and then to increase your level of knowledge. Then here you have astaxanthin, all these activities, high performance HPLC, or you have liquid chromatography to do the characterization. You go for FTIR, which you will be doing a demonstration, or you go for DSC to characterize all those biomasses, you know, in different by different techniques, so that every process is completed. Yeah. And then cytotoxicity, biological activity or bioactivity. Yeah. So, you can make things complicated from primary processing, secondary processing, all the way to tertiary processing. Yeah. Now, if you will see this particular process, Slowly I have to bring in now the technology, because subsequent lectures are going to be the technology, so that you are able to make a link from the previous one. Yeah. This is ongoing experiments, ongoing work at the moment. Shrimp shells, hydrochloric acid, wash water. Yeah. Instead of using 1:20 straight away, first to use 1:5, take it away, use another 1:10, take it away, so that you are not building the concentration in it. Yeah. So, number of times you can do the extraction. Instead of doing one single extraction, you can do it multiple times. Something like you are drying your papadum or papad, leave it at one point, it takes longer. Turn it around, it takes less time. You are drying clothes, you keep turning upside down. Wheat drying, you keep churning it around, so it dries faster. Very similar protocol here. Yeah. So, instead of going for 24 hours, we can reduce time significantly. Alkali, and you get your chitin. So, even the conventional process was improved by using different combination of it. A. B. Instead of doing couple of hours with ultrasonics and microwave together, this was a specialized equipment which I will show it to you in maybe tomorrow when we go through a new technologies. Is specialized type of equipment which was designed, and within 10 minutes whole the process was done within 1 hour. Yeah. So, that is the place where we use the technology to improve processing efficiency. Yeah. And as you can see, these are different colors of the product, what is obtained, and raw material, ash content and protein content. Conventional, ultrasonics and microwave, recovery yield. Yeah. So, you are able to reduce the process in a shorter duration. So, this is the way it shows how we can use different technologies to improve the processes. Now, any questions or any suggestions or anything related to shells? Yes.
Sir, if we use soft shells instead of hard shells, can we get the same amount of chitin?
Soft shells means which one?
These crustaceans like crab and shrimp lose their hard shells, right?
Yeah.
Sometimes. So, if we use their soft shells, will they have the same amount of chitin as hard shells?
But why it will have a soft shells? With the certain varieties, they have a soft shells. Yeah.
No, they lose their hard shells at a time.
Yes. Yeah, they lose because of demineralization, and that is one of the problem of environment, because of changing the pH of sea water, and the shells are not as strong as they should be. Some of the chickens, they have very hard shelled egg, because their diet contains lot of calcium. If they are deficient in the calcium, the shells are weaker. Yeah. But the chitin, chitosan will be there itself, that will be there, and again it has to be investigated how much you are going to get. So, the whole problem with the climate change is acidification of oceans. Because of acidification, the shell's strength is not as much as it should be. Very similar, if you do not have too much of calcium diet, your bones will be weaker. Yeah. But protein and other content will be the same. Yeah. So, this is very similar. You will get similar one, but it will be very difficult to say unless and until we identify how much chitin or chitosan is there in raw material, and the whole of this biorefinery depends upon your recovery methods and how much you can recover. So, if shells in biomass contains 10 grams of chitin, and you use all different extraction technique, as you can see the recovery yield. Yeah. If you are able to recover all 10 grams, your recovery yield is 100%. Yeah. Whereas some are not recovered, based on that you calculate your purity, recovery yield and extractability. Yeah.
Thank you, sir.
Any other question?
Sir, from this table, why we get zero amount of ash content from conventional method?
Okay. Now, in this particular one, 0 and nicely spotted, that was never measured, so it was not required to have a 0. I wanted to see, I just add some number. I already told you that I will leave some of the mistakes, yeah, to see how many people are spotting it, how many are not spotting it, yeah. 0 means nothing here. It was something like a blank here. Okay. It was not estimated. Only thing was to compare, because already done, to see this. There is no, it cannot be 0, yeah. Okay. It was just added in. I added this 0 this morning. Okay. That's good. So you are awake. Yeah. So basically, when we compare with different methods, and moreover when you are able to demineralize everything, yeah, when this is basically to find it only related to the protein. When you get 100% demineralization, it has to be 0, but it won't be 0. And as you can see, if you add this part, if you add this plus this, it makes it 100. Yeah, that means demineralization is not complete. If you remove everything, all the minerals are gone. Yeah, that means ash should not be there. Correct? What is the purpose of demineralization? Ash contains minerals. Yeah. So if you remove all the minerals, yeah, that means ash should be technically 0. Yeah. So, but it cannot be absolutely 0. It was some 0.02 or 0.03. I just deleted the rest of the word. Yeah. So this shows the conventional method what we are trying to improve with ultrasonics or microwave to have 100% demineralization, but demineralization was not 100%. Yeah. So the purity of chitin was not as great as conventional one, but the process was done in 20 minutes compared to 8 hours or 6 hours. Yeah. Did I answer your question? Any other question? There is a logic, you know, if you can't convince, confuse them. Yeah, sorry.
Sir, whelk shells and other crustacean shells are differing in chitosan content. What about the composition of oyster, clams and mussels?
Okay. Oysters, scallops and all those shells, they have different levels of proteins, chitin, chitosan and calcium content. Yeah. So first thing is, did not investigate almost on all the shells. Yeah. That could be assignment for you to do all the shells. The first thing, if you see the establishment of biorefinery, to see the biomass, what all it contains and what are the value of those ingredients, and then to establish the process. Yeah. Okay. So they all contain, pretty much every shells, they contain some amount of proteins and a calcium network. That's why they have a harder shells. Yeah. And if you cannot use it for food purpose, one of the best application of these shells are also to make a biomaterial, that is, which can be replacing ceramics as well as cement as well as a construction material. Some of our collaborators in Queen's University Belfast and other, they are using it as a filler material for construction. Yeah, because these shells can also be used for making construction material. So that's one, is to see the composition. They all have different varied level of composition, and if you open any standard book or any standard paper, you will see all those composition. That again depends upon the variety, as your colleague mentioned about soft shells, where they are grown. If they are coming from the deep water, they have harder shells. If they are grown in less nutrient, the same thing like a wheat crop may have different amount of protein content. Yeah. Same thing, all the shells, they have a different composition, and whatever is their composition, and depending upon that composition, you are going to get your final product. So what we covered here was basically some of the repeat of the biorefinery processes. You have a raw material, then you have a process, and then you have end product. Yeah. So the end product, what you get, now comes the next question, what is the quality of those end product? Yeah, as you have seen here, how it compares with the commercial one. If you are growing crabs only to obtain a chitosan from a crab, you are not interested in meat, because some of the bigger businesses, every business does not have a food angle. They throw all those meats, they only use it for chitosan production, because chitosan is commercial processes and provides significant amount of money compared to the food itself. Yeah? And that is why if you will see the waste hierarchy, is the feed energy is the lowest one, well, disposing it to the waste, least one, then you have energy, then you have food, then you have feed, then food, pharmaceutical, cosmeceuticals. Yeah? So, that particular triangle. So, lot of places all these shells are grown only for the production of chitin or chitosan, and this is going to go more and more, because these chitosans are going to be used for making biodegradable polymeric material, like what we use PLA film. How many of you know about PLA films? Polylactic acid, coming from where? Lactic acid. Lactic acid is a part of yogurt production. 40 years ago, who thought that lactic acid will be used for polymer? Yeah? Since chitosan, they are long molecular weight compounds, they can be used to make a packaging material which are very durable, strong, as well as can replace your single use plastics. So, that is why the more and more emphasis are going on side stream. So, if you take full biorefinery approach, you solve not only the food problem, but also tick boxes for every sector. But remember, you cannot establish a full biorefinery that you want to do a PhD on biorefinery of shells. Then you have to see each and every unit operation before you talk about the full biorefinery. Yeah? You know, one single experiment itself optimizing chitin production, then you have astaxanthin, then you have a protein. Yeah? So, there are number of PhDs has been completed, number of postdocs they have completed to establish one single biorefinery for seaweed. It took almost 5 to 6 years to have a full biorefinery established with the seaweed, which we will cover in a next lecture. Okay, so with this we conclude today's one, and we will see it in afternoon. Yeah. So, so we will start, and this is number 13, but which is to do with the zero waste biorefinery of aquatic plants. So, main focus on this is going to be related to macroalgae, some bit on microalgae, and not including other plants. It could be duckweed and different applications. It pretty much will be repetitive. So, essence of the message is how we can establish a full length biorefinery. And if you have any questions or anything, or so just feel free to send me an email or this address, and I can respond you back. Yeah, or this is my TEAGASC one, and another one is at ucd.ie, Brijesh.Tiwari at ucd.ie. This is the university where I am adjunct professor, so it is not my main position is in TEAGASC, that is Irish Agriculture Food Development Authority, and also at UCD. So, if you have any question, feel free to ask. So, what we have covered so far was all to do with the biorefinery, establishment of biorefinery, that is raw material, processes and the end product. Some examples were there for related to crustaceans and shellfish, and you have already done some bit of practicals related to that. Yeah. Now, we will start with the seaweeds, that is macroalgae. So, if you remember how we produce macroalgae, if you remember last lecture, lecture number 10, where was the production of macroalgae, you have thick rope and there is one small string is attached to it, yeah, all the spores, and slowly this grows just like a plant, and this is known as holdfast, and then this is the seaweed which starts growing, and afterwards, and this is one small ball which is suspending this particular rope into water, and then after 5 months, 4 to 5 months, and you get this much of biomass is produced. Yeah. So, this was all to do with the production. So, production is quite clear and straightforward, and you will see even if in wild harvest, if you cut it, again it grows on the seashore. It is something like every time you cut a grass, then also keeps coming in. That is a natural phenomena. So, this is if you will see, the key benefit is marine primary producers contribute 50 to 71% of carbon fixation. So, if you see the carbon cycle, nitrogen cycle, phosphorus cycle, what we have studied in our school times. So, this fixes the CO2, and CO2 sequestering potential 36.2 tons to 500 ton CO2 per hectare per annum. You can see what is the huge potential of CO2 sequestering. That means all the CO2 from the environment is absorbed by this seaweed. These values are significantly varying. What could be the reason why we do not have one specific value? Answer is simple. Alaria esculenta will have different potential, vulva will have different potential, vulva lactum, Lemnaria digitata, Saccharina latissima, sargassum. So, number of different species depending upon the geographical location that different species they grow. Based on that, this is amount of CO2 they sequester. Yeah. That means balancing out is carried out by ocean. So, we can presume that is the reason why we have more of ocean, less of land. Yeah. Because whosoever when the earth was created, they would have thought humans will remove all the forest. So, let us keep more water so that they do not make extra buildings on water. Yeah. So, this is what it proves, how it can sequester CO2. And what are the inputs required here? Nothing. You can't do any fertilization you can't put any fertilizer in ocean. So, basically this is what way macroalgae is cultivated, and these are some of the key benefits. And we already covered economic benefit of seaweeds, economic benefit where all it can be used. So, I wonder why do you not have a question why we call it as a weed? What is a weed?
Waste crops that grow with the crop plants.
Correct. So, here why we call it seaweed? Is this correct name? Somebody questioned that one, why we call it seaweed. It should be better called as a sea greens, yeah, or macroalgae. Yeah. So, weed is basically, you are right, weed is any crop, unwanted crop which is grown with the main crop. For example, if you have if you are growing wheat and if you will see some millet plant, that becomes as a weed. Yeah. So, basically it is not right crop, but at wrong place. Yeah. Now, other day we were discussing about the blanching. You all suggested different ways of blanching, why we do blanching with the carrot, potatoes, drying another one. Now, if you will see here, these are the two seaweeds, same Alaria esculenta what you saw in the previous one. If we do not blanch it and dry it, it becomes this color. Yeah. If you blanch it and dry it, it retains its color. Yeah. Make sense? So, that is one of the reason why I led the discussion on blanching. So, I have to incorporate that blanching to see how it is related to this particular course. So, blanching followed by subsequent processing, or after blanching you dry it and then you can use it directly as some sort of product. That is all depends upon your culinary application and your own skills, how you can make different types of food product, and you can be as innovative as you think. Yeah. So this was the growth, and then comes first unit operation, that is processing or stabilization of biomass. You blanch it and then continue with the processing, blanch it, you dry it, continue with the processing, or taking a fresh directly for drying. So drying can be of multiple ways. Simple one is, what is extensively used is hot air drying. You have a biomass, you clean it because it contains a lot of salt on the surface and a sand. You clean it and then you dry it. Yeah, you blanch it or you don't blanch it, and then amount of energy required and time required. Now these are quite advanced techniques, that is ultrasonics for drying application. So when I cover ultrasonic tomorrow for technologies, then you can see what does it mean by airborne acoustics. So far if you have seen ultrasound system, they all need a liquid as a medium, but in majority of sound frequency you don't need a medium, air is sufficient enough. Yeah. So depending upon the frequency. So some of the system which requires air as a medium can be used for airborne acoustic drying or fluidized bed drying. It is very similar, that you have hot air blowing through a bottom surface, there are pores there, and then product is in suspension. So that is fluidized bed drying. So all those drying techniques we evaluate not only based on time and based on how much energy it is consuming. So this microwave drying is not the domestic microwave what you use. This is a commercial scale microwave drying. Even the domestic microwave can also be used for drying. You would have seen when you cook anything in a microwave, you get that smell outside. Yeah. So if you create a vacuum, that means fix a vacuum pump in a microwave, and now don't try that one at home to cut your domestic microwave and start taking the vacuum out. No, it's quite dangerous. Yeah. So but it can be done by a professional, and you take a vacuum so that it takes the moisture away. Yeah. So that microwave can also be used for drying, or microwave based on conveyor. Yeah. Or else seaweed directly goes through another type of cavitation, that is hydrodynamic cavitation. This all will be covered when we go on to the technology side, and then to use directly from the fresh one. Yeah. And this seaweed can also be used directly for food purposes, and then we will discuss when we go for value chain. That means you can have mixed with rice another one, or with different biomass to make alternative fish type vegan product. And if you remember in the first few lectures, we were talking about how we can make direct product or different application, direct food product, food ingredients, feed ingredients, and biofertilizer, biopesticide, number of different compounds can be obtained. So the focus here is energy efficient drying. That means the focus is on reducing the energy and stabilizing the particular biomass. So fluidized bed drying is as you can see here, this is just a hot air blowing from the bottom. Yeah. And you have a product here, and it removes the moisture, and what you see it on the top is basically a transducer, ultrasonic transducer, which can be used for improving the drying process and maintaining the quality. When we go through the technology section, you can you'll have a better clear picture. And then all these drying processes has to be optimized. What should be the flow rate, what should be the temperature, and what should be the duration of, and to what level you want to dry. You don't have to dry everything to 5% or 4%. Yeah. If product is stable at 15% moisture or 13% moisture, that's sufficient enough. Yeah. Drying purpose is A, to reduce the microbial load and to improve the shelf life. If you want to dry it and keep it for 1 year, you bring it to low moisture. If you want to keep it only for a week, you don't have to bring it to 5%. Yeah. So all those things has to be tailored based on end product application. Yeah. So your definition or to your answer to the question should depends upon what is your intention. Yeah. It is not you want to use a technology because you want to look fancy. Yeah. So that is why it is very important to know your objective before you select any given technology. So any questions so far? Okay, how many of you have eaten frozen pea? Garden pea. Okay. How it is frozen? Oops. Have you seen IQF, individually quick frozen? Yeah. What is the process? Anybody? All those masters who are doing MTech, they know this answer definitely. Freezing of peas and garden peas, how it is done? Frozen product, what we get in the market, how it is done with the liquid nitrogen, right? So liquid nitrogen temperature is minus 196 degrees Celsius. But if you put anything at minus 196 degrees Celsius, it will crack. Yeah. So how it is done? That is fluidized bed drying or fluidization for freezing. So fluidization means what? So that means any solid product can be given a property of fluidization. So like water flows in a form of liquid, that is fluid. If the same dust particle is going in following a fluidization property, is called fluidization. So you have cold air going through, very similar to fluidized bed drying, and the product is getting exposed to the cold energy, so it gets frozen. Yeah, it's very simple. Fluidized bed drying is not, it's not a rocket sciences. Same fluidization is also used for freezing your product. That is IQF. That means individually quick frozen. Yeah, and then you control a temperature minus 30, minus 40, which can improve the freezing properties. By doing so, you are retaining the structure of it. If you do slow freezing, ice is having a tendency to coalesce together and ruptures the cell membrane. Yeah. Why I am moving from macroalgae to pea, or yesterday we brought in potatoes? Because blue is not separate. Yeah. Everything is interlinked. All the different processing technologies are interlinked. So one is the principles of food processing and other one is application. So you study the principle and you apply those principles to make a technology. So that's the fundamental difference between engineering and a technology. In engineering, you study the principles, yeah, and in technology, you use those principles to develop system. That's why we call it civil engineering, mechanical engineering. Yeah, we don't call it a mechanical technology. Yeah, agriculture technology is one thing, agriculture engineering is another one. So the principles remains the same, application changes. Now, if you take as collection here together, fresh seaweed which is harvested, washing and grinding, yeah, to different size. Either you vacuum pack it, you do salting. I am not going to go into details of this one because there are certain IP is related to that. We have our own certain patent where the farmers or the seaweed processor can preserve a biomass for up to 1 year without having any energy added to it. Yeah. Or blanching, you pack it. So this is pretty much the experiments what you carry out. You know, if you have to do an experiment on different technologies or developing a biorefinery, you have to follow certain protocol. So this is coming in from one of the recently completed PhD, Shanglu Zhu. Now he's gone back to China and to use it for high pressure as well. High pressure mainly if the seaweed is used directly for food purposes and to check the stability, and then also to see the microbiome profile. Microbiome is microbiological profile of those seaweed, and that will also vary from the area where it's been grown. And as you can see, this is what you have seen. Yeah, very same location, and this is the man who was collecting the seaweed, and he was the one who was doing this particular work. Yeah. Now, after this, give you some of those images here. This is the seaweed salting, yeah, packed, high pressure treatment, hot water, blanching process. Yeah. So here blanching process was done 70 degree for 5 minutes. So whatever temperature you are using, 80 for few minutes or 70 for 5 minutes. Those who are in dairy processing, what is the pasteurization temperature of milk? One person on a mic, sorry. Yeah.
72 degrees Celsius.
Very precise. 72 degrees Celsius for
2 to 3 seconds.
2 to 3 seconds. Any other? Take the mic, please.
72 degrees Celsius for 15 seconds, sir.
For 15 seconds, yeah? Okay, any other?
$63 degrees Celsius for 30 minutes.
60 degrees Celsius
63 degrees Celsius for 30 minutes.
Okay, for?
30 minutes.
For
half
30
an hour.
minutes, okay. Now, this is correct, yeah? This is correct, but this is called thermization process. Lethal temperature is 70 plus, yeah? If you take apple juice, that is also heated to 72 degrees Celsius for certain seconds and time, yeah? To inactivate what? Which one? Spoilage, so pathogenic microorganisms, yeah? That is the definition for pasteurization. In pasteurization is a process, is not a technology, yeah? Pasteurization is achieved by high pressure, microwave and different technique, yeah? Not lot of time I do hear that it is called as pasteurization is a technology. No, pasteurization is a process, yeah? So you only focus on killing pathogenic microorganism. This is a thermization process to stabilize the milk for certain time. 72 is a lethal temperature for microorganisms. So you heat it for 72 degrees Celsius for 15 seconds, yeah, that is correct. And if you have to go for 2 to 3 seconds, it is 75 for certain time, 80 for some seconds. It is all to do with the time and temperature combination. How much weight, where is our Pushpa? How much weight you can handle? How much weight a person can, Mike, how much weight you can hold?
80 to 85 kgs. Also.
80 to 85 kg. Now the unit I'll put how long, for how long?
Maybe 15 seconds or 20
15
seconds.
seconds. So he really took himself as a Pushpa then. So 82 kg for 15 seconds, yeah? If weight is reduced to 20 kg, yeah? So you can hold it for 1 hour, yeah? If weight is reduced to 1 kg, you can hold it for a year or something, yeah? So 100 kg also for the fraction of second. It is all time and temperature combination. Temperature becomes meaningless if you don't add time to it, yeah? But there is a caveat. If you put milk at 40 degrees Celsius for 2 days, all the microorganisms will grow, yeah? So you have to go for a lethal temperature, yeah? So any of the technology which can achieve microbial safety of a product at sub-lethal temperature, if you are able to kill those pathogenic microorganisms at 20 degrees Celsius, 30 degrees Celsius, are classified as non-thermal technology, yeah? That is the difference between thermal technologies and non-thermal technologies, yeah? Is it clear? Do you want to add anything to it? So definition is quite clear. Any technology which can achieve microbial safety at sub-lethal temperature. That means there is a lethal temperature and a sub-lethal temperature, yeah? So 70 plus is always a lethal temperature. So you have to cook something for 72 degrees Celsius or above to kill most of the microorganisms are killed at this temperature. So same thing comes for sterilization. What is sterilization?
Complete destroy of all microbes.
All microorganisms, that is spoilage and pathogenic. So for that again you will see UHT process, ultra high temperature, 180 for few seconds, 121 for certain seconds. So that is basically to achieve sterilization, that means to eliminate all the microorganisms, that is spoilage and pathogenic. So when you pasteurize it, during that process certain spoilage microorganisms are also inactivated. So sterilization principle is also based on you inactivate certain spores, yeah? When you mentioned about non-thermal technology for liquid food, we have to achieve 5 log reduction, yeah? Any technology which can be used as non-thermal for food application should be able to achieve at least 5 log reduction, whether it's milk or juices, yeah? Now this is very high level of population, microbial population, that is 10 to the power 5 CFU per ml. Yeah, this is 5 log, correct? Because log of 10 to the power 5 is 5. Now, in order to inactivate this much amount of bacteria, if it is normally present in any product, it will spoil within couple of minutes. Yeah. So, why the definition is the technology should be able to achieve 5 log reduction? Simple answer is, if you can jump 5 meters, you can definitely jump 2 meters. Yeah. So, if technology itself can jump only 3 meters or can achieve only 3 log, it cannot be classified as non-thermal technology, right? But this is mainly applicable to liquid foods, not for solid food. No technology or majority of technology cannot achieve 5 log reduction in a solid product. Even if you do chlorine washing, maximum you get 1 log or half log. Half log, that means 50% removal. The sanitizer what you use, if it says 90% removal, 95%, right? If you read the sanitizer during COVID time, all the sanitizer will say it will remove 99% of microorganisms. Lifebuoy 95% or 90%. What is it? 1 log. Yeah. So, 5 log is a big number. The purpose of this is mainly because if you are able to achieve 5 logs, then definitely you are able to achieve 2 log. Yeah. So, just get your concept very clear. Yeah. You may hear different definitions, different places, but that was the fundamental of pasteurization and sterilization. That will come back again tomorrow, yeah, on the lectures. That is what I deviated a bit on that one. So, fresh, washed, chopped, so this is all your primary processing. Same thing happens also with the shells one. Yeah. Shells one is quite different. You wash it, you clean it, you take a whole biomass or you take a side stream. So, this particular one is unlocking the potential of seas and ocean, not talking about the side streams here, yeah, talking about whole biomass. So, these are all different values of hot blanching, salting, pressure, what are the changes in log CFU. Yeah. So, as you can see, the reduction is only 1 or 2 logs. Yeah. So, if you are interested in knowing further, I can send you those documents, you can read through. That was not the main purpose of showing you all this data sheets to see how much log reduction happened. The purpose is, if you want to stabilize a biomass, at the same time to improve the processing efficiency, to use a technology, for example, high pressure, it also improves the extractability and also preserve it for certain duration of time. Like what, when we use supercritical, that also improves the yield of chitin, chitosan, at the same time we get our pigments. Now, this is seaweed biorefinery. Yeah. It looks quite complicated. I will simplify it. If animation would have done a better job here, but seaweed, you dry the seaweed, that is pre-treatment or stabilization, extraction, recovery and final product. Yeah. Process 1, this particular seaweed by using clean and green solvent, that means solvent which does not contain, are not of chemical origin. Well, all are chemicals, but not of mineral acid or to get a greener solvent. Hydrodynamic cavitation, that is cavitation because of water bubbles. I will talk through this one tomorrow when we go to the technology. After that, you do membrane filtration, 10 kilodalton, that is ultrafiltration, and you spray right, you get laminarin or mannitol. Mannitol is a sugar alcohol, low molecular weight sugar which is present a lot in seaweed. Yeah. Mannitol can be an alternative also for xylitol, which is used in chewing gums as a low sweetener sweet. Laminarin, that is fibers, that is a product, and this laminarin is also known as or classified somewhere as beta glucans, similar properties. Beta glucans coming from seaweed, this is a soluble fiber. Yeah. But this comes in is water soluble, but for that you need to disrupt a matrix. So, we are disrupting a matrix by using this particular technique. Yeah. This will be very clear when we go into exact alginate production process and then how this can be used. The residue after that, that means if you draw parallels with your crustaceans, when you added your acid, you get acid soluble fraction. There were certain pigments will be there, yeah. Sugars are not there in shells, but low molecular weight compounds are there. That is your proteins are coming in, sorry, calcium chloride, another is coming liquid suspension, and that you can separate it by using membranes as well. The residue, similar treatment. Now you go for higher level of ultrafiltration to get alginates, yeah. Second product, the residue, isoelectric precipitation, and you get your proteins, and then leftover biomass you get as a fiber, yeah. Commercially, all these seaweeds are used mainly to produce alginates. All the alginates what we get, seaweed for alginate, seaweed for carrageenan, seaweed for agar-agar, and all these are gone as waste products. So, this is one of the way of establishing the biorefinery, and you get all different ingredients out of seaweed. So, that is protein, fiber, laminarin, mannitol, alginate, and this fiber can further be broken down by using a specific enzymes like cellulase, viscozyme or so to get your sugar in a form of glucose, and that can go for your ethanol production, yeah, or leftover biomass goes for bioenergy, yeah. Remember that particular circularity diagram, number of different value chains coming out. So, you have biomass, stabilization, processes, and then end product, yeah. So, that is one of seaweed biorefinery. Now, this is another seaweed, that is Chondrus crispus. This is known for providing carrageenan, which is used extensively in ice creams as an stabilizer. This is very simple process to extract carrageenan. You have a seaweed, conventional process is you heat it from 90 to 110 degrees Celsius for 4 to 5 hours, yeah. Whatever comes into the water, you separate the water, it forms a gel, you dry it, you get your carrageenan or agar-agar. Agar-agar, somebody mentioned about gelidium, it was you, okay. Gelidium is used for agar-agar or carrageenan from Chondrus crispus. So, once, and this contains up to 30 to 40% and in some cases up to 60% of carrageenan in this biomass. Leftover is your proteins. So, if you remove a carrageenan, which is if you remove carrageenan, which is around, suppose if you remove 50% of carrageenan from seaweed, 10% of protein becomes almost 5 times, yeah. So, when you remove it, so other biomass you can get it easily, your you can easily get your protein. So, drying, extraction, all these are ultrasonic probe, bath system, high pressure, pulse electric field, enzyme, and all these technologies will be covering it tomorrow when we go into the processes, yeah. And then once you get that, either you use alcohol for precipitation, you dry it, you get a carrageenan, or else you precipitate with alcohol, you dry it in oven or sun drying, you get your carrageenan. Then you get a solid biomass and you grind it. So, if you take a starch, if you make if you cook your starch, it becomes like a gel, yeah. And if you dry that gel and mill it, that will be again the starch, but gelatinized starch, yeah. Something like you have a rice, you have parboiled rice, that is partial gelatinization of rice. So, very exactly the same process, and then whatever residue is left over, you can get proteins and then residue fiber. So, alginate process is quite complicated, agar-agar processes or carrageenan process is quite straightforward. Now, all these things in between 1 or 2 steps are missing. One is sometimes this particular seaweed is washed with formaldehyde or methanol just to remove the color, bleaching of the color with formaldehyde or using methanol, but in that process the residue become useless. You cannot use that because formaldehyde is no longer used as a preservative or used for any purposes. Yeah. So, all the usage, how do you know it is correct? So, anyway, so that is the process for chondrus crispus or to get carrageenan or to get agar agar from gelidium. Any questions so far? No? Okay, how many of you have done extraction or used ethanol for, sorry, you have a question here? No? Okay, that is okay. You have used alcohol for precipitation. If we make a solution of a protein or if we make a solution of gums or beta glucan or fiber, the moment we add alcohol, it precipitates. Yeah? Even in milk, if you add alcohol, it will precipitate. Can anybody explain why alcohol can be used for precipitation? And yesterday I was discussing this with some of you. Why ethanol can precipitate any of those compounds, whether it is carrageenan or fiber or a protein. Ethanol is same as alcohol, which is sold in pubs and bars. Yeah. All these carrageenans, protein, all they are also classified as hydrocolloids. Yeah. That means they form a colloidal suspension when they come in contact with the water. Yeah. And the moment you add ethanol to it, ethanol is having greater affinity towards the water. It draws out all the water from the biomass and molecule precipitates. So, one of the important aspect of food processing operations for ingredient to eliminate the usage of alcohol because of multiple reasons. There are some social aspects are there. That means alcohol should not be used, A. B. Alcohol handling in industrial premises is also risky because it is highly flammable liquid. So, how we can make a process which does not require alcohol or how we can eliminate the usage of alcohol. So, alcohol is used extensively for precipitation only because it is having higher affinity towards water. It draws out all the water from the hydrocolloid, that is colloidal suspension, and leads to the precipitation. That is why if you read into any of the paper for extraction, easier one is to precipitate by using alcohol. An alternative to alcohol, even though alcohol is a green chemical, it does not harmful chemical which can be easily removed by evaporation or so, but how do we replace ethanol? That is another important question. So, this previous two was all to do with aquaculture. Again, this is the company what pre-treatment, extraction, and you will see some of those one other day when we give ultrasonic treatment. This is an SCM image which shows, which improves extractability of it, right. Clean and green solvent, you get sulfated polysaccharides, that is fucoidin, and you also get laminarin. Now, this is specific to a specific seaweed. Every seaweed will contain those biomasses, those ingredients, but at different level. Fucus vesiculosus, it contains large amount of fucoidin, and this is used extensively for making lot of different type of pharmaceutical drugs. They have antimicrobial properties as well as antiviral properties. And then residue, you get alginates, byproduct for protein and a fiber, and fucoxanthin is very similar to astaxanthin, which is responsible for the color in seaweed, is a sort of carotenoids. And to extract that, you need to have supercritical fluid extraction system, like what we get it from astaxanthin. Now, then once you get all this fucoidin, then you have, if you will see here, fractionation by using a membrane system. That means very same ingredient is broken down in different molecular weight to measure all the biological activities, including cytotoxicity, in order to see which side of product is okay for pharmaceutical properties. Yeah? And breaking down large molecular weight compound into smaller molecular weight compound, again technologies can be used. Okay. So, this is another way of biorefinery. That means once you get an ingredient, how you are going to make into different types of product or value chains. Now, if you look at this, this is a commercial process for obtaining alginates. This you can find it any of FAO document or any of the old tradition, any old book you will find it out how to produce alginate. You have a seaweed, you wash it, you grind it. Doing the washing with hydrochloric acid or calcium chloride, that is acid treatment in water to remove all these impurities. Yeah. Then you are what you are doing the moment you add acid to it, alginate present in that particular biomass is converted into alginic acid. Yeah. Once you have alginic acid converted, you add alkali or sodium carbonate. Na2CO3, NaHCO3. What is the difference between these two? Mike. In the front row. Okay.
Sir, one is carbonate and one other is bicarbonate, sir.
Correct. That's what even lady in the front was also saying. Sodium carbonate, sodium bicarbonate. Now it becomes trickier when what is then NaOH?
Sorry, sodium hydroxide, sir.
How it is prepared?
Base.
Have you heard about Solvay process? Yeah. It is technically prepared from this one, right? Sodium carbonate process and a salt. You put electric charge, you get chlorine away, CO2 away, and you get sodium hydroxide. Yeah. So either use sodium carbonate, sodium bicarbonate, or alkali. You can get sodium alginate. Yeah. So there are multiple number of variation. Some process you will see to use 2% of sodium carbonate, some places sodium bicarbonate. Important thing here is you have to have a sodium, then only you can get sodium alginate. Yeah. If you use KOH, potassium bicarbonate, potassium carbonate, you will get potassium alginate. Why only to make sodium alginate? We can also make potassium alginate. Do you agree? Simple. It's not being done all the time with sodium alginate, and you can have different properties depending upon your end application. That is the way new type of product ingredients are discovered. So sodium carbonate, that is alkaline treatment, and then you remove residues, and original processes pre-extraction is up to 18 to 24 hours seaweed is mixed in acid condition. You remove acid, you wash it. Then after washing, bringing the pH to neutral, then again 18 to 24 hours in alkaline solution. Then you get your residue, which is again a waste. This is again a waste. In this process, I haven't included your formaldehyde or methanol, because that is also carried out in certain production processes if they are using it for laboratory microbiological medium, where you need to have a specific color and other. So, number of different variations are there. Now, you get sodium alginate, yeah, solution. One is you precipitate the sodium alginate by adding alcohol to it. Yeah, that is simple. And then you get a purified sodium alginate. Then you dry it, mill it, pack it. Other one is the moment you add calcium chloride to it, yeah, it will form calcium alginate, which is not soluble in a water, and it precipitates calcium alginate, and you can pack it, and whenever you want to convert it back to sodium alginate, add acid to it. Yeah. So that is calcium alginate process. Third one is adding HCl, flocculation, alginic acid, adding again the carbonate, and you get this. Yeah. So what happens, why we are adding salt, and in some cases when you are looking into this process, certain places again sodium chloride is added. The whole purpose is alginate present in a seaweed is not in a separate box that you have a key and you take it out. It is present in different salt form, calcium form, magnesium, potassium, and you convert everything into sodium alginate. More and more sodium is there, more and more alginate can be recovered out of matrix. Yeah. Now, so we had a task how we green this particular process. Now, this BioRBIC is basically a bioeconomy research center, and acronym is BioRBIC, that is dot BioRBIC, and this is a center which was now in second phase, valued across around 60 million, where 20 million is coming in from industry, 20 from European Commission and through different projects, another 20 from Science Foundation Ireland, that is a national research agency, and the purpose is to have the collaborative projects with industry to solve the real problem, right. So, our task was how do we green this process. That was very easy, we just changed the color. Yeah. It was red, now it is a green. So, greening the process, that means how do we make it zero waste and how we can utilize every fraction. Yeah. So, normal alginate process, you can get it from any of those any of the processes, and if anybody is this is one of the book which we did almost now 10 years ago. I can send you the PDF copy if you do want, and you can have a look at it. Yeah. That is a conventional method for this one. First, dried seaweed, first intervention. This shows how we can deploy a technology at different stages depending upon our end intention. Energy efficient drying technique using microwave, airborne acoustics or different technology which can dry the product quickly. A. Second one is stabilizing the fresh biomass and utilizing the fresh biomass. Why we have to dry it and then add 1:20? If it is wet, so you may get away with 1:10. Yeah? Do you agree? That was the first intervention for stabilizing, that is involving new technology to stabilize this biomass. Second one, the counter ions and impurities. So, these are not basically, it is very similar to weed, right compound but at a wrong place. So, these impurities are laminarin, that is soluble fibers, that is your one value chain. Amino acids, it contains lot of free amino acids, and fluorotannins, that is again the phenolic compounds of seaweed are fluorotannins, like what you get different bioactives like anthocyanin, quercetin, caffeic acid, all these are phenolic compound. Similarly, seaweed also contains phenolic compound called fluorotannins. The only difference is these fluorotannins are long polymers made up of fall glycinol. So, that is like a single unit, and they also have lot of antimicrobial activity. Here the main compounds are laminarin and amino acids, because they contain certain type of amino acids which can also be used as a flavor enhancer like umami flavor due to the presence of glutamic acid and all those acids. Yeah? That is different types of value chains. I will be coming back to this particular once again when we deal with different types of value chain. Next one, algal residue. So, very similar, when you just think of the experiment what you have carried out in a lab, where you have leftover biomass, here you have a protein and algal fiber. Yeah? And these two can be further separated by using either enzyme which can break the fibers or protease enzyme which can break the proteins into peptides. Last one here, solvent, to remove alcohol, to deploy membrane technique to separate alginates. So, this is the way how different interventions are carried out for different improving the production process, and by this we can utilize every fraction. So, what will be left over byproduct? Come on, you know there is something is left over. Pushpa. Yes.
So wastewater will be the side stream.
Yes, the wastewater coming or the processed water over here, and if you are using ethanol, I do not call it as waste one, because same ethanol can be reused again, because ethanol recovery is easier by using a simple rotary evaporator in a lab or distillation system. Yeah. So, alcohol can be reused multiple times. Yeah. So, that is the water which can be used for the production of other biomass. Is this clear? That is why I named it as value addition, using better what we already use. There are a lot of companies within this country also they make alginates. They get the seaweed, you purchase a seaweed and do the extraction. Think if you start growing the seaweed using aquaculture or collect a seaweed and to see what all it contains, you can make your own production process for carrageenan and alginates. So, that is why everybody now focuses on unlocking the potential for seas and ocean. We did not in India, we did not look into it because already a lot of food is there. Think of the countries where only they are very temperate, very cold countries, or the place where there is only ocean. So, they have to dependent only on seafood. Yeah? And if you see the demography of the country, all the population living across the coastal area, their diet includes seafoods. In northern part, it is all vegetables and crops are available. So, it is all to do with vegan. Something like rice becomes important towards south, north is wheat, in Ireland it is potato. So, a staple crop depends upon where and when, where do we live and how we or what we have been consuming from generations to generation. And now it has been also classified ethnic food or regional food. So, this is all what wanted to say here. Now, if you go back to this particular website of the company nutramara.com, this was started with all the work which was carried out in TEAGASC. Fucoidin is commercially available, algal fiber, oil from seaweed, it also contains 3 to 5% oil, carotenoids, beta glucan, that is your laminarin, and phenolic compound. So, it is a complete biorefinery, that is a commercial business running, and this particular fucoidin is now available in Brown Thomas as hand cream, and that particular any of those hand creams or cosmetic products which are used extensively, they are quite expensive. 100 ml or 100 grams of that particular tube cost nearly about 80 euros. Hand cream or facial cream or all those things, whatever is used for cosmeceuticals purposes. So, this is one of the most expensive ingredient which is available. If you search for the price, 1 to 2 grams will cost nearly about 500 euros. Yeah. So, you can think of how expensive this particular product is. And you can extract, depending upon the seaweed, Fucus vesiculosus contains nearly about 2 to 18% of this fucoidin, and this was a side stream and was a waste of alginate production process. So, that is the way full biorefinery, and this is fairly stable established business on full biorefinery. Yeah, it is not all the theoretical, this is real business. That is why I went ahead to do full scale description of biorefinery. Same thing can be established for any given crop, whether it is potatoes or cauliflower or any other crop, you can establish the full biorefinery, obtain different fractions. Yeah. What you have to do is take example of potato, look into the papers how you extract potato protein, look at the paper which shows how to extract potato starch, look at the paper which says how to extract soluble fibers or oligosaccharides or fructooligosaccharides from potatoes, and if you match all these three papers together, side stream of A is required for B and for B to A. Yeah. So, sweet potatoes, they are now so all you know your inulin, fructooligosaccharides. How many of you know about fructooligosaccharides? This is short chain sugars. that is having 3 sugar moieties, 4 sugar moieties, and they all are considered as prebiotics. Yeah. So, if you look into those paper and try to come up with the process, you can establish your own biorefinery. Yeah. So, it is not that you start thinking everything from the scratch, and then try whenever you carry out any of your experiment, make sure do not throw your residue, you keep it, and then try to see how best that can be utilized. That means you do all this thing with open mind, not in a rush to finish it. You have to submit the paper, you need to get it published. Hurry makes worry. So, you have to think it properly and you can achieve much better results and outcome. Now, this is the biorefinery concept which has been established for macroalgae based on all the experiments, all the work carried out to date. Yeah. This is a blueprint of any given seaweed. Macroalgae has been worked on Alaria esculenta, Lemnaria digitata, Saccharina latticema. These are 3 commonly grown seaweed in Ireland even through aquaculture. First one is conversion, dry process, the whole seaweed dried. Another one extrusion, which I will cover it again when we go for the product. Make it either feed for kettles, contains proteins and fibers. Fish feed, because automatically fish, they do eat this seaweed, but in aquaculture or pond system or land based cultivation, they do not get a seaweed. To grow insects on it, and insects means to get your insect either as a food. I know insects are now approved for food purposes, but insects are also good source to get chitin, chitosan, and as well as oil and a protein for different non-food applications. Other one is your chicken. Yeah. So, and then once you have this is for feed purpose. Other one, this is already used for bakery product. You have seen some of the examples I showed you when we talked about seaweeds, or having a snacks product. Wet whole seaweed through cavitation, that means converting the solid biomass in a form of slurry. That means if you have any dried product, whole of the potato, if you make a slurry of a potato, you have a carrot, make a paste of a potato. Same thing is done with seaweed. What this will take lot of energy. It's easier to do with the microalgae or a duckweed, but when it comes to seaweed, since they grow in ocean, they can resist very, very high pressure. As you would have seen in that video, seaweed are at the sea bed, 20 meter, 15 meters down, and every meter what is the pressure is a huge. Yeah. So, since they are able to resist that pressure, that means their structure is very stable. Cavitation, then to use protein, alginates, dietary fiber. You saw it from the previous biorefinery slides. Yeah. Then bioactives, fucoidin, laminarin and amino acids. Yeah. Still what is left is your sugars, that is mannitol and certain fluorotannins, and you have a fermentable sugar either using these fibers or certain leftover sugars to produce 2,3-butanediol or succinic acid. These are not for food application, but these are the biochemicals which are required for other non-food applications. Yeah. And then still you have residue goes for biogas or for bioenergy purpose. So, this is the blueprint. Now, if you remember, there was an assignment given. Yeah. So, with this you all have to, because I have been told and you will have some bit of evaluation on it. Here, leaving the seaweed, any of the biomass, you try to establish a biorefinery chart, and for every step whatever you suggest, why and how. Yeah. Does it make sense? You can take a fish, you can take duckweed, you can take potato, you can take mango, you can take anything. Yeah. Establish a biorefinery concept for to develop a zero waste strategy. Yeah. The reason I am not asking you to do only on a seafood one, just because some of you are the purpose of this module is not only for blue economy, also to see how you can translate these concepts to other crops of your interest. Yeah. So, that is what is your assignment. You have to just either type it or you write it on a paper, and then deadlines and other details will be told by your other instructor who have been involved in practical classes. Yeah. So, come up with it and just write why you are suggesting it and how you are going to do it. Yeah. And taking care of new technologies and other elements. Yeah. Be as innovative as you can. The moment you enter into this building, you will see there are 2 or 3 boards. You have one face, create your another face. The boards which are saying some sayings. Yeah. There is one more saying, tell the people what to do rather than how to do, and they will surprise you. Yeah. So, I am only telling you what to do, but you have to write answer to these questions. Yeah. Any given biomass, take it example as egg. Yeah. Egg, shells you have already done, and you get your protein, egg powder, removing lipids or different fractions. Yeah. Try to establish a biorefinery, and even for microalgae or whatever species you can write in and what all can be obtained. Microalgae and only from production, if you are taking a new crop or you have a biomass, say for example microalgae, and how you can establish this. Yeah. Is easy enough assignment. Now, this was a biorefinery concept for microalgae. Microalgae, growth, harvesting, fractionation and different ingredients. All these ingredients will dependent on the type of species what you will select. This I have already covered, so I am just going through the next one. Now, integrated biorefinery concept for microalgae. Yeah. That means all the wastewater, whether it is from seaweed, processing or other processes, you use it for cultivation, you harvest it. After harvesting cells, you disrupt it and you do different type of extraction techniques. Cultivation and harvesting together, cell disruption, extraction. Cultivation, harvesting and cell disruption together, extraction. Cultivation, harvest, cell disruption and extraction. It is pretty much the same number of processes can be done together. You must be having lot of question with this. Yeah. One, you cultivated in a water, you centrifuged it, collected your algal cell. Yeah. Use ultrasonics, solvent to do the extraction or give an ultrasonic treatment to disrupt the cells and then extract your compounds. Over here, while cultivation itself, in a tube it goes to a harvesting system where cells are suspended at the bottom. You recover that cell in a continuous harvesting and cultivation system, then follow the same process. Other one, you cultivate it and then afterwards doing harvesting, that means you have 3-phase separator centrifugal pump, you get your solid cells and that goes straight to the cavitator or along with the ultrasonic directly, it is harvesting it and disrupting the cells. That means, if your cells are in liquid suspension, there itself if you break the cells, you can carry out the extraction. Like what we discussed, you have fish, paste, cook it, oil is separated. That is again depending upon the biomass. Yeah. This is all comes with your own creativity. Cultivation, harvest, cell disruption and extraction. Yeah. So, any of the creativity you do, that is all the innovation you bring it in. Yeah. I have seen lot of different type of posters and presentation in different conferences within India. I can bet you there are lot of new ideas are there. The only problem is that is not taken to the terminal end. Yeah. You create an idea, you talked about it, you got a poster, somewhere you got an award and then you forget about it. Yeah. Having an idea and taking to the terminal end is very important. That means you start something, try to finish it at the, get the finishing line. Yeah. So, that is all to do with integrated system for biorefinery. We were working on one of the system called with the Mint, with couple of our industrial partners from Central Europe. Microalgae integrated technologies, that means the whole system itself was produced, wastewater was going in, it was growing the microalgae like a big container, and then you were fractionating all the compounds, and there was integral technology, was hydrodynamic cavitator in it. Yeah. Cultivation, breakdown of the cells, and separating different ingredients. So, all these things can be done together. So, application of microalgae, some of these things I will be covering again when we go for a product. So, now onwards in subsequent lecture you may see some bit of overlaps. Yeah. Microalgae, whether they are grown in your bioreactor or a funnel. So, they are different species. This is Cholera vulgaris, Purium porphyridum, and then is Hematococcus, and this is diatom or so. There are different species are there, and they all have a unique feature. If whole of this red one is directly dried and they have very good solubility, or you give a technology treatment and their solubility profile is improved and used directly into the food product as a food coloring agent. You know, we get red color laddu, yellow color laddu, you know, all those type of food colors are added, and all those are chemicals, and that can be used straight away for coloring. Yeah. Either use a conventional technology, pre-treatment, or clean and green one, you get phenolic, sugar, polysaccharides, proteins. Even if you take a water soluble fraction of it, then you have perfect color. Yeah. You have seen spirulina, the moment you put in a water it turns into green. Same way, if you have red microalgae, you drop it into water, even 0.1 milligram, the water turns red. So, that means that is again can be used for direct color, and this color is because of phycocyanin, that means color bearing proteins. Proteins, they have their own colors. Yeah. So, based on that it can have a direct food application, that is the easiest way to do it, or you carry out different application or purification. Now, conversion of microalgal biomass, fermentation. This is one of the process where you have cultivation, you harvest it and you add your microbial culture to it, or you add your enzymes to convert carbohydrate using microorganism, Clostridium, Saccharomyces cerevisiae. What is Saccharomyces cerevisiae? Yeast. It's where it is used? Fermentation of beer, bread and everything. Yeah. Yeast consumes sugars. Yeah. And that yeast can also be used for fermentation. And some of the bacteria what you see here, Clostridium botulinum is one which is used as a botulinum toxin in milk. Yeah. Similar type of species, Clostridium, Aspergillus niger, other microorganisms including Acetobacter, and all those microorganisms are used for fermentation to produce a specific type of compound, even to make bioethanol or biobutanol. One work was there in a project waste to fuel, where a lactobacillus bacteria was modified. If you know the glycolysis, we did cover briefly the glycolysis. The glucose is converted into pyruvates. Yeah. Every microorganism does it. If you modify the microorganisms, instead of making pyruvate, it makes lactic acid or butanol, and butanol is better fuel compared to ethanol because of its stability. Yeah. Like a butanol. So, that is all the interventions which can be done. Anaerobic digestion, organic matter using bacteria for biogas. Hydrogen generation. Now, we all are talking about hydrogen as a fuel for different engines. So, it's cold tea. So, that means we get biohydrogen or esterification to get biodiesel. These are all microalgae for production of energy related compound, gasification, syngas, bio-oil, biochar, bioelectricity. So, these all are energy related application of microalgal biomass. food ones we have discussed a lot and will continue those discussion, and these ones which does not have to be of food grade. So, if you are using a wastewater to grow microalgae, then focus could be all to do with energy, because moving forward energy is one of the most expensive element going to be in near future. So, the possible biorefinery, algal biomass, antioxidant, pigment, minerals, protein, food, fertilizer, cosmetics and healthcare, lipids, lipid free biomass, and then biogas fermentation transesterification. Yeah. So, this is a possible biorefinery for any given bio, microalgae or macroalgae. It is easy to draw it on the sheet. When you start looking into it, then you need to think of what is the solvent, what are the external intrinsic factor you need, and then you get one ingredient. Yeah. But if you have long term vision that you want to establish a biorefinery and then you build individual processes, then you are able to cover it. Yeah. Remember, Rome was not built in a day, it takes time to build it, but all the unit operations has to be optimized to make a full biorefinery. Yeah. That itself could be a long term research career objective, that you want to have a zero waste biorefinery system or algal biorefinery or anything, and this is the time where you can start thinking about it. So, again microalgae, macroalgae or duckweed. Some of the duckweed aspect I already covered it and discussed a lot of example about water soluble proteins and what was the water soluble protein in duckweed? Rubisco. Yeah. Rubisco, enzymes, all these are source of protein. Multi-product biorefinery, that is growth, harvesting, pre-treatment, treatment or extraction, food, additives, pharmaceutical, cosmeceuticals, energy. If you get a feed, also you are solving a food issues. If you develop a cattle feed, or if you develop a chicken feed and or insect feed, insect goes to chicken and chicken produces your food product. Yeah. So, these are all, that is the reason the arrow was added here. Now, remember this related to your assignment. Yeah. This is a common term, how we can establish a biorefinery. Any given biomass, post harvest operation, pre-treatment, that is blanching, drying, milling, fractionation, treatment, mechanical, biochemical or chemical. Wave means basically a sound waves. Yeah. So, you have mechanical, chemical, physico-chemical, all these treatments, you get your biomass. Then you have to think what could be the end product. Yeah. What are your target end product and what are the target waste or byproducts generated for that particular one. If you take here as seaweed, your end product is suppose alginate. Yeah. What will be your waste product? All the residues, laminarin, amino acids, soluble fiber or so. Yeah. You identify that, you test whether this all is present or not, what compounds are there, likely cause of it, measure recovery and repeat your experiments. Yeah. This is your input variable. This is specific compound testing efficiency of a process. Yeah. How you can improve that particular extraction yield or recovery yield of your target compound, and how you can reduce the waste if it is produced, how you are going to recover it. Multiple compound, novel process, optimizing a product, and then you will be able to establish your full biorefinery. Yeah. Does it make sense? So, I know I went very fast on this. One is your raw material, and with this raw material what type of treatment you can do to stabilize it. Yeah. Or raw material you may not need any treatment, you have a biomass. What is your end product? Alginate, protein, fiber or any of those end product, your main target product, and you look for what are or what is the composition of waste streams or byproducts generated, what all it contains. Once you know that, that means you are looking for a specific compound, and if this is an expensive compound or it is having high value ingredient, how you can optimize to extract that particular compound, and looking for all other biomass so that you can establish a zero waste, and then you think what all is there, whether you want to extract a calcium out of it, selenium is there, zinc is there, ash is there, or you have lipids are there, oils, different amino acids, and then try to establish a recovery. Yeah, that means what are the methods how you can enhance the recovery of that particular targeted compound, and establish all the factors which can increase its recovery, or if you are able to increase the recovery of this, you are damaging the byproduct or waste coming out of it, and then continue doing the experiments. Yeah. So, this could be a simple blueprint for your thesis itself. Yeah. And now, if you divide this thesis work into different chapters, 1. Pre-treatment strategies for stabilization of biomass, A, done. Other one, extraction of protein from seaweed, different techniques, different methods, you get a protein, measure its amino acid profile, DSC, FTIR, and what all you are doing, that is 2. Third, valorization of waste coming out of protein production system. So, that means you keep your samples there, yeah, your chapter number 3, and then characterization of that, yeah, characterization of this, characterization of all your main product and co-products, chapter number 4, and everything joined together to do life cycle assessment or mass balance, then makes a comprehensive study, comprehensive thesis done, and each chapter has gone as your either as an IP to file a patent or processes or publish it. Yeah. Remember, finding a solution is always a IP. If you find the solution, if you get a process to extract protein from micro or macro algae, that is an IP. Studying the solution or studying the problem becomes your publication. Effect of temperature, ultrasonic frequency, and all those can go as an literature. Yeah, that means you are adding it to the literature. Yeah, that means so that other people can follow it. Yeah, but whenever you go target for any publication, think your long term goals. Yeah, because whatever goes in a publication media remains forever. Today you want to get the publication very quickly so that you clear your thesis and all. 20 years down the road you become a director or a vice chancellor or anything of any institution, and if there is some loophole in that particular study, all your well-wishers will take it out. See, he became so and so, and this is the work he was, this is the way he got his degree. Yeah. So, to avoid long term issues, you have to work from the beginning with punity. That means whatever you do it, whatever you get it, and if your experiments are proper, you can withstand it. Yeah. Somebody says, no, that is not possible. No, it is possible. This is the way it is possible. So, it should be based on F, A, I, R principle, right? F for failed, my Pushpa. Findability, A, accessibility, I, interpretability or interoperability, yeah, that's same, and R, reusability. Yeah. So, any of the work what you do, and if it is on a publication domain and somebody is not able to reuse, you are not doing justice to the science A, and you are wasting public sector money. Government spends huge amount of money on research to create a knowledge. If you are not using it properly, that means you are not doing justice to the money. Yeah. Any questions? One easy one is to how to establish a biorefinery. Yeah, that's very straightforward. 2, unit operations. end products and how we can estimate the properties and different technologies, and this is the focus for tomorrow, to use the new technologies and to create value chains. Yeah. So with this we conclude today's one. Yeah. And if you have any question, feel free to ask now or later on.